Um, yes, please type your attendance once again. So I will have to start my lecture because it's already 10 a.m. and yeah, we have only very few minutes. That is 40 minutes or so only. Try to finish that within that. So today we will talk about this diode equation. So I think some of you might have heard or might have seen the diode equation also. Uh, we will just uh, try to obtain the diode equation. We will try to describe the necessary theory, the necessary concepts behind formulating the diode equation. Okay, so this is our p-n junction. Yeah, we know that in the inside there are free electrons. There are free electrons associated with pentavalent atom, free electrons, and this is a junction like we discussed. So the electrons from those pentavalent atom near the junction are diffused towards the p side, and they transform into positive ions and negative ions, thereby forming a space charge region. We also know it as a depletion region. And on the p side, uh, for every trivalent atom, there is an associated with, sorry, there is an associated holes. Trivalent atom will be associated with holes, and they can accept free electrons from the inside. And yeah, here the majority charge carriers in inside is majority charge carriers, like we discussed before, it is electrons. And the majority charge carrier concentration in inside, we denote it as Nn. And we also say that there, due to thermal energy, there is a minority holes, So the minority charge carriers are holes, and the concentration is given by P subscript N. And on the p side, we have majority charge carriers as holes. So holes have a concentration denoted as pp. Minority charge carriers in the p side is electrons, free electrons, and the concentration of such minority free electrons is denoted as np. N for free electrons concentration, P is a subscript, means free electrons concentration in the P region. Now, if you connect a battery like this, that such that the positive terminal of the battery here is connected to the P side, negative terminal of the battery is connected to the N side. This connection is called forward biasing. This connection is called forward biasing. Here, under this connection, when you connect the positive battery terminal to the P side and negative battery terminal to the N side, this external battery will give sufficient, this external battery will give additional energy to the free electrons on the N side. And with this additional energy given to the free electrons here, the free electrons may be able to overcome the potential barrier here. So we have said that there is a built-in electric field and there is an associated potential barrier. Okay, so these negative ions on the p side, they will repel any further diffusion of free electrons. But if you connect external potential like this will give additional energy to the free electrons from the inside, and the electrons from the inside can diffuse towards the p side. And once the electrons are transferred to the p side, it will result in electrical current, transfer of charge, electrical current. And similarly, when you connect the positive terminal of the battery to the P side here, this positive terminal will give energy to the holes here. So holes also can diffuse holes also get diffused towards the n side, and thereby resulting in transfer of charge, and that transfer of charge results in electrical current. So under this electrical circuit connection, which we call it forward biasing, we can have current across the PN junction. So like I said in the yesterday's class, without any external biasing, the current without any external biasing, the current due to electrons and the current due to holes across the junction, they are zero without any external biasing. If you have a PN junction as it is, PN junction without any external connection, there is a space charge region, positive ions, negative ions, negative ions, negative ions. So this will have sufficient built-in potential, we call it VB, and this built-in potential prevents any further diffusion of free electrons to this side and diffusion of holes to this side. So the built-in potential, in the absence of any external circuit connection, battery connection, it prevents current across the PN junction. Therefore, the current across the PN junction is zero without any external potential supply. Now, here we are dealing with a condition in which we connect the external battery to this P side and N side, and this, as I just said, will result in transfer of charge from the N side to P side and from the P side to N side. Oh, hey, kapu class ka lak lo tu ka lo ko la thei cheng e. Knowledge is power. Oh, thật nó sợ chưa? Parliament can it happy. Oh, nia có tiếng đó có riêng với mẹ rồi. Rất tiếng đó cũng. Trời tôi có tiếng cái là có riêng tiếng nghe mà riêng chủ giờ lắm mà. Lâu bel treo mẹ rồi thì kan point score treo mẹ. Là. So, yeah, what I was saying, yeah. So when we have this external connection, it results in transfer of free electrons to the n side, to the transfer of free electrons from the n side to the p side, and transfer of holes from the p side to the n side. So in the p side, this was your concentration of free electrons. Sorry. I got carried away because of that telephone. So on the n type, on the n side, the concentration of minority holes is this Pn. But under forward biasing, you are transferring holes from the p side to the n side. So that means you are, in addition to this, you are adding some amount of holes in the n region. Okay, in the n region you are adding additional holes. So when you are connecting the forward biasing here, you are transferring holes from the p side to the n side. That means if Pn was the concentration of minority holes in the n side, under forward biasing, after transferring holes from the p side to the n side, you are increasing the concentration of holes in the n side. And similarly here and similarly here Np. Np is the concentration of electrons. Np is the concentration of electrons, minority electrons in the p type on the p side of junction. But when you do external biasing like this, you are giving energy to these free electrons, and these free electrons, by gaining energy from this external potential source, they will overcome the potential barrier and they will move to this n side. So you can assume that there is addition of electrons on the p side. You can assume that there is addition of electrons on the p side from the n type, n side of the junction. Therefore, the number of free electrons on the p side, that is np, will increase by certain amount np. Yeah, let me repeat that statement. So without any external biasing, no transfer of charge across the p-n junction. But once you connect this external biasing, the electrons on the n side will gain energy from the potential source, and they will overcome the potential barrier that we discussed across the junction. By overcoming this potential barrier, the electrons from the n side, some of them will cross over to the p side. And let's say the amount of electrons crossing over to the p side is given by this. So NP was the minority charge carrier concentration in the p side. So the concentration of electrons in the p side will increase by del NP. So del NP is the amount of electrons, free electrons, transferred across the junction. So this transfer of charge contributes to electrical current. And also similar to that, when you are connecting positive terminal to the p side here, holes on the p side will gain energy from the positive terminal of the battery. By gaining energy, they will overcome the potential barrier due to these positive ions. So by overcoming this potential or repulsive force created by these positive ions, holes from the p side will move over to the n side. Some amount of holes from the p side will move over to the n side. So that amount of holes which move over to the n side is what is given by del pn. Del pn is the amount of holes transferred across the p-n junction. So this contributes to hole current across the p-n junction. Contributes to hole current across the p-n junction. And you know that Pn is the minority charge carrier concentration. So once you transfer some additional holes from the p side to the n side, Pn value, the minority charge carrier concentration in the n side, increases by exactly that amount, del Pn. Okay, I hope you understand up to that point. Now, yeah, here as you see here, this side on the n side there is a positive, on the p side there is a negative terminal. So the potential barrier is such that the polarity is such that this side is positive, this side is negative. That means when you are connecting this external battery, the external battery will have opposite polarity in comparison to the potential barrier. Therefore, the resulting potential across the p-n junction is denoted as VB minus V, because the polarity of this external potential V is opposite to your barrier potential. See, the barrier potential is this side is positive, this side is negative. However, in this external battery, this side is negative, this side is positive. So the connection, forward passing connection, is such that VB, the potential barrier across the p-n junction, is having opposite polarity to the external battery. Therefore, the potential, effective potential across the p-n junction is VB minus V. That you should know, right? Now, there is this relation called Boltzmann relation for electrons and holes concentration, which again we will directly use. So suppose you have a n-type semiconductor, and here as again Nn is the majority charge carrier concentration, and Pn is the minority. So Boltzmann relation, yeah, and if it forms a junction with p-type semiconductor here, if it forms a junction with p-type semiconductor here, and in this p-type semiconductor majority is pp, minority is NP. So the Boltzmann relation gives the relation between majority electrons in the n side and minority electrons in the p side. So this ratio is given by exponential of E VB upon KT. KT is the thermal energy. KT upon E is the thermal energy, and VB is your barrier potential. Okay, so depending on barrier potential, Boltzmann relation gives the concentration of electrons in the n side relation with the concentration of electrons in the p side. And similarly, this is certain classical calculation which we do not need to do in this class. So the Boltzmann relation for holes is that PP is the majority charge carrier concentration of holes in the p side. Pn is the minority holes concentration in the n side of the p-n junction. Here VB is the barrier potential. So when you form a p-n junction, this is how the carrier concentration will relate. That is given by this Boltzmann relation. Now, as I was saying, under external biasing, once you transfer holes from the p side to the n side, we have said that this Pn value increases by del Pn. Del Pn is the amount of charge transferred, holes transferred. Okay, and under external biasing, we simply replace Vb with Vb minus V. Vb with minus V, like I said before. And here you can just do some simple mathematics like equation, when just transfer this and multiply and all. And then after that, this is what you will get. Okay. And from this relation to itself, Pn can be written as Pp exponential of minus of EVB upon KT from this relation to. Then you substitute this PP value here in place of this Pn, then you get this expression, and then if you take the common factor, this is what you will get. Del Pn, as I said, this is a Pn junction. This is a Pn junction. Del P, you are by connecting external battery like this, you are transferring holes to n side. Del Pn is the concentration of holes which is transferred from the p side to the n side. And as I said, the minority carrier concentration is here is Pn. So by transferring this much amount of del Pn holes from the p side to the n side, you are adding the concentration of minority here, just like this. Okay. So del Pn is the amount of holes transferred across the p-n junction, or the amount of holes which is contributing to whole current across the p-n junction. And similar to that, you can do the same calculation for the electrons. So del NP, and then eventually you will get this relation. This is the same thing only. Del NP is what? You have a p-n junction here, p-type, n-type. You have large number of electrons. Once you connect the battery like this under forward biasing, some of these electrons will move towards the p side. So those electrons which are transferred across the p-n junction is del NP, which is contributing to what is called electron current. This amount of charge that is transferred across the p-n junction contributes to electron current. Okay. Now, once we know that, you can write the current across the p-n junction like this. J is the current density, and like we defined before, current density is simply current upon cross-sectional area. We already discussed what a cross-sectional area is. Now the current density is simply E N V E plus E P V H. That was what we discussed. Like the current density when we discuss, if you just browse your notebook. This is what you will get. And here in this case, the actual amount of electrons that is contributing to current is the amount of electrons that is transferred across the p-n junction, and the holes that is contributing to the p-n junction current is holes that are transferred across the p-n junction. So holes that are transferred across the p-n junction is del p-n, like I said here, if you recapture this. Okay, so therefore I can write the current across the p-n junction using the amount of electrons that is transferred across the p-n junction, holes that are transferred across the p-n junction, and you can put the value of del p-n and del np like we calculated here. Okay, so if you put those values and after simplification, you will get this. So you will get this, and this quantity, this whole quantity is known as reverse saturation current IS. This whole quantity is known as reverse saturation current IS. Okay, so this equation is what is known as a diode equation. Diode equation. This equation predicts the electrical current across the p-n junction under biasing voltage, various biasing voltage. Now, now we talk about the forward bias. So let me draw it like this. So this side we call it forward bias. Forward bias. In forward bias, the voltage is taken as positive. Voltage is conventionally taken as positive. Forward biasing voltage is taken as positive voltage. We call it VF, let's say. And this is the current. And we said that in a p-n junction, p-type, n-type, there is this potential barrier VB. So when you connect external forward biasing voltage plus minus, this is your VF, let's say, forward biasing voltage VF. When you connect like this, if the voltage is below 0.3 volt in the case of germanium and below 0.7 volt in the case of silicon, there is practically no current, no detectable current. Current is in few microamperes only. Microamperes means 10 to the power minus 6 amperes. So here in this case, you are not having any electrical current conduction due to the transfer of electrons from the n side to the p side, nor the transfer of holes from the p side to the n side. This transfer of majority charge carriers, that is electrons from the n side to the p side, holes from the p side to the n side, does not happen below 0.3 volt if you make your p-n junction with germanium crystal, below 0.7 volt if you make your p-n junction with silicon crystal semiconductors. The current does not, the current due to this transfer does not occur. The reason is that your forward voltage VF is in this region. Your forward voltage VF is less than your barrier potential. If your forward voltage is less than your barrier potential, then the energy given by this external forward voltage to the electrons is not sufficient to overcome the potential barrier VB here. Therefore, it cannot climb over the potential barrier, and the electrons cannot be transferred to the p side, and no electrical current due to transfer of majority electrons from the n side to the p side. And similarly, the potential given under this biasing voltage, which is less than the barrier potential, you are not able to transfer holes from the p side to the n side. Okay, and but beyond that, beyond this, the current is given by this equation. Okay, the current is given by this equation. So it's like this. The current across the PN junction will be IS exponential of EV upon KT minus 1. So when your voltage V, here in this case we use VF, forward voltage VF, just to indicate this as a forward voltage, let us put subscript F, VF. Well, if your VF is greater than this, beyond this, your VF is greater than your barrier potential, then electrons will start float across the PN junction from the N side to the P side, and similarly holes from the P side to the N side. And current will increase according to this exponential function. So if you increase the value of this VF, current will increase exponentially under this expression. So instead of having a straight line, there will be exponential increase of current like this. Okay, exponential increase of current like this according to this equation. VF increasing means exponentially your current will increase like this. Now, let us consider another situation in which you reverse the polarity of your external battery like this. So instead of this is P type, this is N type, instead of connecting like the previous configuration, let us reverse the polarity. So positive, negative. Positive is connected to the N side and negative is connected to the P side. So the voltage supply is what we call as VR. And by convention, reverse voltage, we call it reverse voltage, reverse biasing voltage. This reverse biasing voltage is taken as negative, Therefore, the effective potential across the PN junction VB minus V will be VB minus of VR. So this will be VB plus VR. So the external biasing voltage will add to the barrier potential. The external biasing voltage, the reverse voltage, will add to the barrier potential. If it adds to the barrier potential, if the barrier potential is raised, then the electrons cannot overcome, nor the holes can overcome the PN junction. Then you cannot have any practical current, right? So if you look at this expression here, here in this case, we put a minus sign here, okay? In the case of reverse biasing, like I just said. So here simply, your V here is simply what we explain it as reverse voltage VR, okay? So in the forward biasing, this is a plus voltage, plus of EV upon KT. When you have reversed the polarity, you introduce a minus sign here. Okay. Once you introduce a minus sign here, as you increase the voltage, if you look at this exponential term, you can write exponential of minus of EV upon KT as 1 upon exponential of EV upon KT. Now, if V increases here, if V value increases here, this term will falls down to 1. Sorry, falls down to 0. Because the denominator, if V value increases, means the denominator will become very large. If the denominator becomes very large, this term 1 upon exponential of EV upon KT will falls down to 0. So if it falls down to 0, then you can just put this term as 0 here. So by putting this term as 0, the current across the diode will become minus of IS. IS, there is a minus sign here because the current is in the reverse direction here. And IS is due to the minority charge carriers and strongly dependent, and it is only about 10 to the power minus 6 ampere. That means you cannot detect such current using a conventional voltmeter. And we can say that under reverse biasing, no current passes to the PN junction. Okay, so under reverse biasing, see, this side is positive current, this side is negative current. let's say this side is reverse biasing VR, or VR which is negative voltage, OC voltage VF is towards the right hand side, negative voltage VR is towards the left hand side. And here you just see that the current across the PN junction here will be minus of IS. So that means there is a negative current here. A very small amount of negative current will flow like this. Okay. So this is what we call as a reverse saturation current. Reverse saturation current. Reverse saturation current due to the transfer of minority charge carriers. Okay. So unlike a forward biasing, you cannot have a transfer of electrons majority from the N side to the P side. If you reverse bias, the minority, if you reverse bias here, you see that there are majority free electrons here, minority holes, majority holes on the P side, majority holes on the P side, and minority free electrons. So under reverse biasing, negative supply is connected to the P side, means these minority electrons on the P side can cross over to the N side of the junction. And similarly, when you connect positive terminal to the N side here, minority holes will gain energy from this. Minority holes can also conduct electricity across the PN junction. But the minority carriers at room temperature is of very, very low concentration. And because of such a low concentration, the electrical current contributed by such minority charge carriers is very, very small, in the range of 10 to the power minus 6 ampere, which we call it microampere. And few microamperes, it's not detectable, or it's not certain current which is which can be detected by a normal multimeter, or you cannot use it for any device this much amount of current. So it is as good as if no current is passing through this PN junction under reverse biasing. Okay, so here I will stop, and I only have 1 minute. So if you type all your attendance, unless you have any queries, we can stop here. And so what we have discussed so far is we have what is called diode equation. We have a diode equation due to the transfer of charges, and from that diode equation we can explain the IV characteristic curve, IV curve of a PN junction. And yeah, next class I will talk about Zener breakdown, a valence breakdown, and all these things. So this will be for the next topic. Okay, so I will stop here. If you have typed your attendance, you can exit the meeting.